Hello, my name is John McClure. I work for Weldon Pump. Today, we're going to speak about the electric fuel pumps do's and don'ts, common types of fuel pumps, installation and testing best practices, and common issues to avoid while actually working on the pump. One of the biggest things you'll find as you start to work on the pump is that it's very important to understand what the mechanism is, what it's capable of, what are the concerns that you should have while you're testing them, such as bench testing. And that's really what we're going to get into. Who am I? I know it's customary to let you know who's speaking. So I work with Weldon Pump. I've been doing aerospace design and management for over 20 years, well over 20 years at this point. I do quite a few IAs, and I probably have met many of you. Hopefully I've gotten the opportunity to meet many folks out at the IAs in the field, plus these wonderful Concord virtual IAs that I was grateful to be part of last year as well. One of the biggest things to know about Weldon is we're a very old company that takes quality very seriously, which actually, for me, translates into these IA discussions with you folks, because we're trying to pass on not only obviously what Weldon does, but we believe in a certain way of doing things in the industry that keeps people safe, keeps planes flying, and also makes it a little bit more comfortable and easier for the actual people with their hands on the product. We go back to 1918 as a tool company, and then our first plane we ever put a pump on was the B-24 Liberator in 1942. Well, it was made in 1942. The company did win a prestigious E Award in 1944, and it's essential that I bring that up because that is who we are and what we believe in, and that's why we do have this long history with these pumps. And hopefully I can give you some data that I've picked up over the years, and then I love the feedback from you folks to get back to me through the Concord email system that they'll provide to you. Give me some ideas of other items we need to discuss in here, things that you want to discuss more. So please keep that in mind. Love feedback. Weldon is in Cleveland, Ohio. We've been here since the beginning of the company. This past year, we've doubled our space size, modernized our facility. We're an old company that's getting young again, as we call it. In other words, we're getting ready for the next 80 plus years of pump making, and it's very exciting to be here. And it's been a challenge too. So that's the good stuff. But we are AS 9100, full engineering, manufacturing facilities, repair stations. You get it. You're familiar with that type of discussion. We make fuel boost pumps, injection pumps, anything but water pumps. Basically, we don't really do air and water pumps, but we do quite a bit of work with the military and high performance race as well. So that's just something that at every IA that I go to, people ask me about the race cars, and I love that too. So it is fun. It's a fun combination. Here's a few of our customers around the world. We've been fortunate to work with many fine companies, making many different designs and types of pump mechanisms for them, which leads to our conversation in a moment. So it's important to recognize that you might have the same mechanism in every pump company, Parker, all these fine companies. We all make similar mechanisms at times, but there are tweaks that are made for individual fuel systems. Here's our list of some of our GA pump applications that will be more applicable to what we're talking about here. And we work with pretty much all the general aviation OEM, companies. So it's been a good thing for Weldon over the years, and hopefully it translates into this conversation. Oh, just for you race folk out there, I did not have this last year, and I was asked why. So here's some cool images of some of the stuff we're on in high performance Weldon racing. So it's pretty fun. I enjoy going to these. So let's jump into mechanisms of pumps. For the sake of this conversation, I'm really going to be looking at, I'll hit on the gear a little bit, but mostly it's centrifugal, cam vane, and slung vane, because we're talking about electric fuel pumps. But I do leave gear there because it is something we need to recognize and know. And it is important that we recognize that there are gear pumps that come into play here. But for the sake of our conversation, it's really going to be slung vane, cam vane, and centrifugal. So first, what we'll do is we'll take a look at what these mechanisms are, how they operate. And this is so important when we get to discussing the actual testing, bench testing of pumps or troubleshooting of pumps, to recognize what their capabilities truly are. We'll start with the slung vane. It's a positive displacement pump. As you can see on the screen, it's very consistent. It also handles thin fuels very well, which surprisingly some mechanisms do not. They like a heavier fuel. And it's self-priming, which is key to this conversation. We're going to talk about a couple different ones that are positive displacement, which means they can prime themselves. They don't need any help. And then we'll talk about the centrifugal pumps, which if they have their own little impeller inside, they can prime themselves, but usually they need to be mounted in the fuel or below the fuel tank, the fuel head. So we'll get into those now. But the slung vane in particular is exactly what you may think. It's a term that Weldon uses a lot. Some people call it rotary vane. There's quite a few different names for it. This is a Weldon version of it, and what we do with ours is it's designed in a certain way that allows us to not meter fuel, but we can control our fuel flow very well. So in this case, you have a rotor that spins, and it has 4 blades that are part of the rotor, that are in the rotor, that sling out. That's where the slung vane name comes from at Weldon. So you can see the 4 blades here. And as it spins, it'll bring in fuel in these gap areas from the inlet. So as it spins at a very fast pace, it actually pulls and adds fuel into behind these blades, and the blades push it by, forming onto the actual ring wall. And it'll push it and push it and push it. And as it gets to this point, because you have a restriction here, it goes to the outlet, and this is where you form your pressure. That's how, and that negative pressure on the inlet allows you to actually pull not a vacuum for all these, but pull fuel. And that's how the pump primes itself. It actually will start pulling in the inlet, and then it'll allow us to go through the outlet. This section in here allows us to control in many ways how much fuel flow by this gap. And that is the basics of a rotary blade or a slung vane, depending on whose company you're working with. This is a little bit more, I wouldn't say detail, but this presentation will be available to anybody who would like it through Concord, from myself. There is some more detail that I place in these slides that I don't necessarily talk to, because I don't want you to fall asleep too soon in the actual presentation. But the point of this is, you're looking at the slung vane is very rugged. It's a very good pump, very high output. You're going to see this basic style being used by pumps all over the place, not even in aerospace, but just everywhere. The difference is of materials, tolerances, and size, frankly, and then speed capability. For the sake of our pumps, we use a lot of tool steel. So we actually have a lot of durability, a lot of compensation for wear, because we need it to be. Whereas there's nothing wrong with other pumps that may be used as a nylon vane or a plastic or whatever, because it's doing what it was designed to do. That said, it's important to understand what your pump materials are doing and and you make sure you don't put anybody in danger by using the wrong materials and higher pressure, higher flow, higher altitude in particular situation. So I kind of talked through this slide already on the previous one, but it is advanced a little bit with actual piece part names. And if anybody has any questions on that, I'd be happy to discuss anytime with you. Here's some examples of the slung vane pump. If you go left to right, those are traditional Weldon ones. The four here, this one you'll find on multiple pipers all the way up to TBM, this basic style. And then what you'll find also in this one, this is on the Robinson helicopter, the second one from the left. That's been on all the Robinson R44s. And then this one right here is on Cirrus and pretty much all the OEMs now. And then this one right here is a Piper 2V6 type pump. And then you have a Parker version right here, a 1C, I believe it is. And it is, once again, very similar to these internally with the slung vane. Difference is material stack and the valving. But the point is that the actual functionality of these pumps are all very similar when they're slung vane. They're positive displacement. To a varying degree, they can pull not a vacuum, but a degree of a vacuum as they prime. Some do better than others due to the materials and the tolerances that are within them. And I'm sure you've all seen the AFP Dukes pumps in the market, the red pump. Those are as well a slung vane type pump. There's a couple things to keep in mind as you're working on these, and I haven't seen this in years, but as you're working on like a Duke pump or even the Weldon pump, third from the left, excuse me, there's a slight gap in between the actual blue pump end, I'm using that one, the Weldon one, and the silver motor. That's intentional. That is actually no need to tighten that down. It is tight. That is actually a design feature during testing. So I bring that up because that has been asked to me I take notes at every IA of questions that are asked to me, and I like to add them into these conversations as I get the opportunity. So these pumps are very common in the field. I'm sure you've seen it. They are less susceptible to dry run and contamination than like the cam vane, which we'll discuss in a minute. But as any pump manufacturer will tell you, we don't like the pumps to run dry. These are not designed to run dry, just like the engines aren't. And you want to keep the contamination out. But this style is normally a little less susceptible to it. And then next, we're going to move on to the cam vane. The cam vane pump is a positive displacement pump as well. It's very precision metering ability there. Self-priming. We have versions of this pump that can pull a vacuum easily. And it is very good at handling wear. It self-compensates. Now, the key to this pump is there's probably only a few manufacturers still making this style because it's not an easy pump to make. And the materials can be very difficult. The designs are challenging. The more legacy pumps like for Weldon and I think one other company now. But it is a very good pump for what it does. So to give you a feel for what you're looking at here, if you look at this image right here, this is think of a Wankel engine for those who are familiar with it. A Wankel engine, a cam, but it spins, and then you have these two blades that have a retaining ring around these two blades in this image to the right. As this rotor spins, these different high points push the blade in and out. Meanwhile, they're grabbing fuel from an inlet here and moving it to the outlet. Or actually, it's inlet to outlet. This is backwards. So you get the idea. But the point is it's actually doing a similar thing to the other pump we discussed, but it actually has its tight tolerances, incredible metering ability to control exactly the flow you want. And it's very durable as long as it is filtered. It does not like contamination due to these very tight tolerances. So in the right actual installations, in the right usage, these pumps are amazing. But the moment you start to have contamination or mainly contamination or dry run, they're not happy. This goes back. This was our first pump design that was utilized by Weldon in 1942. But more importantly, it's been used by other companies as well. So you'll find them out there. The main manufacturer now, to be honest, is Weldon. But if anybody works with compressors, if you ever open one of those small compressor tanks, many companies, if you look to the bottom, you'll see a pump mechanism that may not look like ours, but if you look at the shape of it, it is actually a Cam Wankel engine type uh, actual metering pump in a way, except for they're only being asked to build pressure within a tank inside that compressor. So in this case, when you look at a Weldon, you can see where ours is smoother, it's fuel, it does all that, but it doesn't mean it's the only mechanism out there. But for the sake of this conversation, let's just keep to this pump. There's thousands and thousands of them out there on general aviation. They have a proven long life. They're self-priming. They're lightweight. Can handle all kinds of liquids. It's really, really good at altitude. There's so many good things. Like I said, though, the biggest thing you want to take into account is inlet filtration is not even strongly recommended. It needs to have the actual filtration in place. And that's mostly to give it its life, let it live forever. You know, these ones that work on unfeathering, for instance, thousands and thousands of hours because it's such a clean fuel. But sometimes clean oil, I should say, when you get into some fuels, if it runs dry or it's contaminated, that's when they lose their life. So these are some examples of cam vane pumps that you may have seen. You've seen from left to right, your Piper, some Cessnas and Pipers, Piper again, all the way up to no, that one actually is Mooney's. Oh gosh, there's so many. And then also this pump right here, you'll see on a TBM, some like the larger Pipers. And then this last one on the far right is a feathering pump, believe it or not. It can be used for fuel too, but a lot of times you'll find them on some CASAs or some military items there. But it is, once again, I'm just going to hit on this again. You just filtration is a must. It's very tight tolerance. And the last I'm going to talk about is the centrifugal. The flow varies with pressure. This is where the difference between the centrifugal is not a positive displacement pump. The slung vane and the cam vane are positive displacement that can pull their own prime and can be mounted well above the tank if with the right materials. But the centrifugal is one that, unless it has a little blade or a little impeller mounted inside, which some of the Parker's Nichols do have, airborne pumps do have on their centrifugals, but most don't. And that's why you'll find them mounted in tank or on the side of the tank or right next to the tank or right below the actual pressure head, because it actually needs fuel into the impeller to allow for it to pump. Great pump for what it does. In no way, just because it doesn't prime, it doesn't mean it's a lacking pump. They're fantastic. They're everywhere. You've seen them. You've worked on them probably. It's very interesting pump. It's not sensitive to contamination in any way. That being said, I should step that back. It is sensitive to contamination because it can, if it's so bad that it impacts the impeller, then you lose your ability to pull, to grab fuel. But compared to the other two I was just talking about, it is less sensitive. So what are we talking about here? We're talking about a higher flow, lower pressure normally, less sensitive to contamination. Fuel will not prime without a positive displacement feature or a separate pump. So if you look at certain Piper aircraft, you'll find that there are, in one example, you have a Weldon in the one part of the wing, and then you have the centrifugal up there, and it's basically Weldon's the emergency pump, and the Parker pump is actually the non continuous duty pump that supplies the engine. And the reason behind that is it could just spin easily, doesn't overpressurize the engine, and it's just a good pump. So, but it still can't prime, so you have to have a secondary feature in case of emergency. And as we look at this is kind of a rudimentary, pretty colorful model here, but it gives you that idea about the flute within the impeller itself and how it grabs fuel as it spins and kind of forces it from a negative on the inlet all the way through to a positive as it goes straight through the outlet of the pump mechanism. To your left, top left of this one is kind of an example of how the fuel comes in through these flutes and then will be released at a higher pressure. So once again, it's an eye chart. But for those who really want to delve into the aspects of these pumps, this is some more detail about how a centrifugal works. We talked about how it induces flow. The basics of it is it's taken from a negative to a positive, like every pump. But in this case, they need to have fuel on the inlet of the pump mechanism because it can't pull its own prime. So what it does is it needs some, like I said, mounted in a tank, on the side of a tank, under a tank even, the head pressure. And you want to take it so that there's always fuel on the negative or the inlet side, so it sucks fresh fuel into the system, and that allows for the impellers to remain full, and then you get a positive pressure on the outlet. Like I said, must be immersed in fuel. If it's not immersed, it's just going to spin. Now the positive of that is if it won't deadhead on a main engine pump because it only provides as much pressure upstream as the actual main engine pump will allow it to. Whereas a positive displacement one can provide that pressure to the main engine pump, and that's where you get return to tank line. Or in the case of most pumps, we have an internal valve and positive displacement pumps that won't allow a pump to overpressurize the system. It's set at a certain, what we call a no flow pressure rating. Centrifugals really don't have that issue, and which makes it very popular on your Bell helicopters, your King Airs, your some items that you'll find them mounted in the tanks, the cartridge canister style, the actual ones mounted on the side, such as the one in the bottom right corner here. This one to the left here is one that's actually can be mounted internal to the actual pump, to the actual tank, excuse me. But once again, a very good pump. These are the three main pumps that I wanted to discuss because they're the ones you'll find, electric pumps, that you'll find on general aviation primarily, and which is what we're talking about. So as we wrap this up, here are the three biggies: slung vane, cam vane, positive displacement. And we'll talk about why I'll be harping on that. And the centrifugal pump is a not positive displacement unless they add a feature internally to the actual pump itself. This is one that I've have a PDF version that I've been emailing out to folks just so they put it up in their shop if they're interested. It's just a nice cross-reference to everything we've been discussing for the past 15, 20 minutes. It is just a cross-reference that talks about what the suction lift capability. Cam vane, it's amazing. Slung vane, it's really good at it, but it's not quite the cam vane. And then the centrifugal, non-positive displacement, has to be immersed in fuel or primed to operate. There are duals available, as I said, that can do that, and it's important to know what those are. Higher pressures. You can. I'm not going to read this whole thing to you. We just went through it, but there are a couple things that I want to push out because as you're testing or if you're troubleshooting, deadheading versus amp draw / cavitation. So the cam vane, if it's deadheaded, it'll have a much higher amp draw, may trip the breaker, less damage to pump due to standard aero relief valve, but you're going to know because your amperage is going to go up significantly. Basically, the same thing happens with the slung vane, just not as quickly, but it will happen. Whereas the centrifugal, you might even have a lower amp draw because it won't cavitate. Simply because it's as long as it has fuel inside there, that thing, it's spinning, it's happy. And as the pressure on the outlet starts to open up, it'll just push the flow out. It's not positive. It's just part of the system. Contamination susceptibility, we talked through that. Cam and slung vanes are it's cam's the worst all the way to centrifugal. Dry run. The centrifugal pump really doesn't have an issue with dry run, but I'm going to tell you every one of their pumps is going to, it has an issue, but it's less susceptible. Let me put it that way. But I guarantee you're going to see something on there that says don't run dry. So In all, this is just a little cross-reference to give you a feel for what the three primary fuel pump mechanisms are in general aviation. So let's get into some best practices and some recommendations. So electrical connections and amperage. One of the biggest things we've been seeing in the last, I want to say 5 years even, has been a lot of splits in wires. And I get it. People have been doing it for decades, and there's nothing wrong with it if done correctly. The problem is we're seeing improper splits that's providing inconsistent amperage to the motors of not just our pumps, but other pumps we look at. It's incredibly important that we understand what the actual current draw is of the actual pump, that if there are line splits to hit multiple breakers, let's say, it needs to be done correctly, safely, and it's not really recommended by us, frankly. We'd rather see a connector utilized than splits. But that being said, we know that it is not unusual in the field. But to give you a feel for what kind of amperage you should expect, you're looking at 3 to 4 amps max for 24 to 28 volt, and about 6 to 8 amp for 12 to 14 volt. You usually run a lot lower than that. That's your maxes, and that's at when you're in full relief, when the motor is working as hard as it possibly can. But I mean, if you're looking at a Weldon or a Dukes or those, and even most of the Parkers, they're going to run way lower. So if you're hitting up to that high amp and you're not in deadhead / no flow, your pump is drawing higher amp. So just something to consider. But from a safety perspective, I just highly recommend, if you're doing splits, just make sure that you're comfortable doing what you're doing, or seek some advice from somebody who's been doing it over the years. Frankly, I'd rather you just put the proper connector on it and call it a day. Insulated ground wire. So this is a thing that's come up in the past, I guess I'm honestly 10 years, but there's been composite aircraft for quite a while. It's not that. It's just all the new fuel systems in certain aircraft don't have the rigidity of the former metal that used to go through, which caused and allowed for multiple grounds throughout the fuel system. And anybody who's ever really worked on fuel systems knows that the fuel line is actually an electrical highway. It is where electricity / static electricity / what you want to call it, static buildup, loves to live. And what can happen is, if the fuel system isn't grounded appropriately, the charge or the static buildup is going to look for a place to live, and in this case, it loves electric motors. So we decided to place, and other companies have too, to give to our OEM customers and our folks in the field an optional ground wire on the actual motor. And we went through to a different coating, and I think it's been very successful. So if you see on ours a green wire, or anybody else a green wire that you don't maybe see, it's optional, but it's simply a ground wire. And for most airframes, 90 whatever %, you're not going to have an issue. It'll tell you to use it or it won't tell you to use it. We just added it because we are seeing much more static buildup heading to the motor over the past 10 years than we've ever seen. So we have made some product improvements to make sure that the customer, the end user, is getting the longer life that we expect from a Weldon, and I'm sure our friends in the other companies are doing the same. But it has been a new world when you start looking inside, and you go quite a few feet without any kind of grounding capability. Mounting. So if you're talking about a positive displacement pump, such as the ones we were talking about, the Dukes, the Parker positive displacements, the Weldons, I'm missing companies, and I apologize if I am. But the point is, the positive displacements like the slung vane or the cam vane can be mounted anywhere. It pulls its own prime, or it pulls its own fuel. So it doesn't necessarily have to be below the head pressure of the tank or a header tank. It has to be, it can be mounted anywhere. The biggest thing we always recommend is have the motor mounted slightly above the actual pump end, because there's usually a cavity between them on these style pumps, and you have your overboard drain pump, which allows for anything kind of, eventually if a seal leaks, it won't go into the motor. It'll go overboard like it's supposed to, so you can see that leak and maintenance it. But also it doesn't go into the motor and start to wear the bearings and flush the bearings, which is what would happen. It's not an explosion issue. It's truly about life of the motor at that point. Whereas a centrifugal pump will want to be mounted in the tank, near the tank, somewhere that it has fuel in the impeller that allows it to actually flow, because it won't prime itself normally. So that's the key to mounting, is just know which kind of pump you have, get it in there in the proper way. Remember, centrifugal needs fuel. Positive displacement doesn't necessarily, but doesn't mean you want to. If it's a pump with nylotron vanes, you probably don't want to go too far away from the tank. But even then, they pull enough of a prime that it should be okay. As we move into filtration, I just wanted to put a few images on here for you that discuss some of the issues that we've seen over the years. And this isn't, most OEMs know this, and they put proper filtration into the system. You have some experimental, that are out there that we always try to remind, and we remind the OEMs too. You need to filter these pumps, not just Weldon's, not just Parker's, Duke's, everybody need to be filtered. And if you start looking at the bottom left, that's a slung vane pump. You can just see the amount of on the spring, there's rust forming. It must have been water in there, but there's also through contamination getting through. And this system design is key for this. If it's a centrifugal pump, it doesn't have as many issues with contamination. So the filtration is important, but usually there's a screen filter on a lot of those, which is sufficient. With any of the positive displacements, you got to look at where you're fitting the elbows. There's so many aspects of this that are very important to the pump. So if it's spec'd correctly, knowing what the system looks like, a pump will last a really good long life. But it's also important that filtration is in there, prior to the pump. A lot of people like to put it on the other side because they think pump positive displacement can't pull through a filter. It absolutely can, and is designed to do so, actually. So filtration is important. Run dry. So we talked about that with the issue with run dry for a centrifugal pump is that you're not going to be able to pump any fuel, which is, I know, seems counterintuitive because you can't with the prime, with the positive displacement, but not necessarily. So if you have a centrifugal pump and you don't have any prime ever get to it or any fuel get to it, it will never start to you have to prime it somehow. You have to get fuel to it. Whereas a positive displacement, as it starts to spin, it's going to pull a vacuum or sort of vacuum that'll suck the fuel to the inlet. The problem is if it takes too long, depending on the mechanism, you could run it dry, which will start to heat up the materials internally. You'll have expansion issues, and you could actually start to blue the actual inserts in the rotors, and they could start to eat into each other when they weren't supposed to, which damages the pump or at least reduces its life. You'll find that with this issue, each different style pump can handle so much run dry. So pump companies are very really don't want to throw a number out to you, but the best rule of thumb is cam vane needs some kind of an oil in it or something as it spins, so that it primes itself, because it's the tightest tolerances. And the more you loosen up the tolerances, the less susceptible to run dry an actual pump will be. And when we talk in a moment about test hookups to test a pump and troubleshoot a pump, that's very important. So installation, some do's and don'ts kind of stuff. Fuel line connection, the right fitting is key. Make sure that, make a phone call to whoever you need to, or whatever's in the manual, about getting the right fitting on there. One of the biggest things we'll run into is pipe dope, which has been used for ever. I've used it on different things. It's not a bad thing. It's just if it's for instance, a pump that we make, if the proper fitting is utilized, you don't need any. It'll seal with the O-ring on the end. Everything's going to be great. But if you do put it on, if you put too much in it, it'll actually get in. It can be pushed into the impeller, and it can lock the pump up. So if it is used, it just got to be very cautious on the outside. But our rule of thumb is don't use pipe dope. It's just not good for it. So the other part of it is if you go to put it in a vise or a clamp, you'll see on a couple different companies have those stickers that you'll see on to the right bottom right that says don't put it in a vise. Why is that? Well, you have magnet sets internal to the motor that they're adhered to the exterior internally to the shell, and if you over clamp it, it actually can crack or loosen the magnet sets or disform the actual housing, which will either ruin the pump or make it not live much longer. And it also, certain ones, if the pump end is actually anything, you could misalign the actual rotor with internal to it with less pressure than you think, because they're not designed for that kind of pressure on there. So be discriminate on how you utilize any vise or clamp, because I know you need to hold it somehow, right? Just be cognizant of the fact you don't want to go too crazy onto these pumps, and then you'll get a good life out of it. So tampering, people love that. This is my favorite part of the IA symposium, is I usually make this slide pop up, and I get the funniest looks from some people like, yeah, obvious, but I guess I need to put it on there still. So, you got tamper seals, you have certain, wiring coatings. If a manufacturer opens something or looks at something and they see that the tamper seal is broken, it avoids the warranty. But also it makes it really, really hard for the evaluator at the repair station to figure out what's really wrong with it, because it wasn't as removed from the airplane at that point, it appeared. That's why communication with whoever you're working with, like if you're calling our repair station, you talk to one of our techs and work through that. But it is, you don't really want to delve into it unless you have the proper tools in the manual there to do it. I talked a bit about contamination with the filters. So here's a few more images. It's a very popular one. The red towel in the middle, the shop towel, we've actually found on a few occasions at least red string wrapped around our rotors inside of our motor. I don't know how it got there, but it's amazing some of the things we find on a pump's returned, and we open it up and pour some sand out of it, or there's been multiple. I can't even get into the list of the fun stuff we found. So this goes back to filtration. 1, no filtration. 2, when working on it, make sure that we're not interjecting accidentally contamination. And then more than anything is water. Sure, you can mount a pump pretty much anywhere in the system, but you don't want it at the lowest level. A lot of times, a positive displacement, simply because that water, if it pools, it'll rust, just like it will on many engine components. It's just good to have good, clean fuel. If you ever take a pump off to store it, what we would suggest is you hook it up to some power, maybe put a cap in the one end, pour any oil, it doesn't matter, pickle oil, as we call it, or ACF 50. There's a nice little thing for them. I hope they appreciate it. And then, or just some motor oil, whatever it is. Get something in there and spin it briefly to make sure that that thing is lubricated and protected while it sits on a shelf if you're going to store it. But you don't want any moisture in there, and you want to make sure there's oil sitting on the actual pump ends. Improper maintenance. So brushes. You need the manuals, you need the tools, but more than anything, everybody who listens to this, they're all very bright and they're experienced. So in a way, I'm preaching to the choir, but I do need to point out there are certain motors that are designed to be worked on and certain that are not. So if you look at the 2 images at the bottom, the one on the left, the brush, there's no brush tap that allows easy access to replace or view brushes. That motor in particular is designed to be replaced or worked on within a proper facility. In many cases, they're not designed to be worked on at all. The brush life, the style of the brush, the commutator, thickness, everything is designed to wear a really nice long life that the original OEM wanted it to, but not necessarily be worked on. Whereas the one on the right in this image has brush gaps, and that one was designed to have the brushes replaced, maybe even clean the comm, and keep going. And it's important to know there is work being done on some of the motors on the left that were not designed. That's being done around the world right now, for that matter, where they're soldering in new brushes, and that's great. Sure, the pump will start running, but the thing to consider on there is it's more than just the brush life. The commutator life is another part of it. The amount of dust that's internal to the pump is another. It's just important to realize and recognize that certain motors are designed to be maintenance, some are not. And it's important that we recognize that. So before I go into these facts, I want to talk briefly about what do we do when it comes to checking a pump. So let's talk about when you take a pump off of an aircraft and you go to put it on a test bench and you go to test it. You got some 12 volts or 24 volts or whatever you need there. When you go to do this testing, the few things that, if you take anything out of this, which I appreciate everybody still listening if they are, I know pumps are exciting, but the things to take into consideration are, one, what kind of pump mechanism is it, and am I damaging the pump while I'm just basically gut checking it or troubleshooting it? A good example, once again, centrifugal pumps. Either it's designed to be in the fuel or it needs to have fuel to it, so that you allow for it to be able to pump. Because you may, if it's not getting fuel to the impeller, you may sit there and go, this thing doesn't work. Well, it's because it doesn't have any fuel inside the actual impeller that'll allow it to pull more fuel. It needs to be primed externally. So that's key. Other than that, with centrifugals, it's just basically on what the manufacturer, voltage is, and then you can, knowing what the amperage should be, and then you can check that pump, but safely, obviously, with fuel going to the actual mechanism. Whereas a positive displacement can be a little more challenging. Yeah, it can prime itself. So if you take it off and you put a hose on the inlet, put it into a small tank, and you hook it up appropriately to the power source, and you hit it, that it should, if it's a very short line, it'll prime itself and you'll have no problem, because there's already usually residual fuel oil within the pump that's lubricating it, both slung vane and cam vane. But if you don't and you just run it for a longer period of time without that fuel, you're damaging the pump. So it's important that with your bench test that you have your fuel readily available, hooked up nearby before you run it. Don't just run them dry. It will absolutely damage the pump over time. What's the time is? I don't know. Cam vanes very quickly, actually. Slung vanes, not so quickly, but why risk it, right? Because what you'll get then is you're not going to know what you're originally troubleshooting. So that's key to know. With positive displacement, yeah, they'll pull their own in there. You don't have to direct prime it, but you don't want to let it run dry for too long. Why is the breaker tripping? Well, it could be a number of things, right? Could be the pump motor assembly is at the end of its life. Could be that there's some contamination within the pump mechanism, causing the motor to increase its amperage. The water, whatever kind of damage to the pump, sitting unpreserved and locking up. These are the common things that we'll get in, frankly, sometimes it's the motor's done. So that is a big part of it. Is there an issue with the motor? Could be. Maybe, every manufacturer works hard to produce the best product possible, but there are, it's a mechanism. Things can go awry. But the key to this is the breaker is tripping. Why? And are you locking up? Is the breaker diminished in its capability? That's another one we'll find. Is the breaker properly sized for the pump compared to its amperage? So it's just truly could be one of three things. It's usually pump life, it's done. An actual issue with the system itself, or you've got something jamming up the impeller internally. So as the impeller starts to get jammed up, it starts to need more amperage because the motor's working harder. Pretty basic. And so those are the main things there. I'm not seeing the gauge pressure. We did at one time. So if you're looking at a pump that has a wound field motor, it actually an older Duke's pump is a great example, and Weldon's made wound field, so I'm not throwing, but those are more common in general aviation. You'll find that they have a slow, steady diminish because of the nature of the actual motor, but they live a long time. It'll live. It's just it doesn't just end. You'll start to see that gauge pressure, whereas a permanent magnet motor, which is used on some Dukes and other Weldons and Parkers, they'll be pretty steady for a long time, and then all of a sudden they'll start to go at a much faster rate. So it's really what is the issue? Which type of motor do you have? But for the sake of bench testing, it's pretty easy. Is the valving internal stuck open? Why is the gauge pressure not there? Is the valve stuck open? Is there contamination, or is it just stuck? There could be a number of things, and the biggest thing to recognize here is just, what does my installation look like? Is it a clean installation? And how is it that I need to bench test this whole thing? Check your amp draw. If your amperage is starting to go either up, usually, you could be slowing down. Your pump just could be going, and that's why your gauge pressure is going. A lot of pilots always tell me it's about sound. They know the sound of their boost pumps. They know the sound of their transfer pumps. And as they start, that pump's making a weird sound now. Well, maybe the motor's starting to go, or there's something binding it. So sound does matter, but it is kind of do you know the sound of your motor? So it's not real scientific. And then I'm going to get into this real quick, because this happened the last 3 IAs. Do we sell direct? No, we sell through distribution. The factory overhauls itself. Same with our competitor. How long should a pump last? This really depends on the usage. So a great example is the almost identical pump is used on a ag plane that is used on more of a personal aircraft. And the personal aircraft guy is getting, the engine life he needs. He's getting a long life of the pump, whereas they're getting 350 to 400 hours on the ag. And a lot of that has to do with the usage of it, how it's used, what kind of pressure and fluctuations of the actual pump speeds, which affects the motor working hard, and then it just the inconsistency. So it's a tough question to answer, frankly. If I knew the specific aircraft to it, we can give the average or what it was designed for. But if it's the same similar pump used in, whether it's an ag plane or a flight school versus somebody's personal, it's very different, and it could be the exact same pump, just what installation were you mounted in. And when should I overhaul it? The standard in the industry is 10 years, but if you check your airframe manual, if you have one for that aircraft, and if it may have an earlier requirement, but it also may just be replaced upon condition. So that means you run it till it fails, right? But we do a standard in the pretty much all of electric pump companies get 10 years MTBO recommendation, by the way, because there are O-rings and seals internally that do have a shelf life, and it is kind of important to recognize that they do have a limitation in how it can actually work. The actual overhaul period is listed here. I threw Weldon's up there because that's what I know, but it gives you an idea of why. It's just like I said, it's seals, and it is a recommendation. So, but unless your actual manual from the airframe says it must be this, this, and this, then that takes precedent. Warranty period, all the companies are different, but you know your warranty, or have your airframe. Whoever needs to know the warranty needs to know the warranty, and they need to know the warranty. We're 2 years on new PMA, 1 year on all overhaul components, and 6 months on repair. And that's from date of installation. That's not date of manufacture. We feel that our pumps, if they're sitting on the shelf not installed, they're not getting time on them. So we changed that a few years back to make it easier for the maintenance facility. And that in itself is my presentation. I'd like to thank the folks at Concord, the good people there, for inviting me to do this and for you listening. And I hope that I was able to say something that was new for you and it didn't bore you too much. But I look forward to seeing you at the shows, at IAs, and feel free to get any questions over to me, and I'd be happy to answer. We like to, because the feedback from the field is essential for Weldon and for myself to learn as I do more and more of these IAs. And I appreciate your time. And thank you very, very much.